Hello. How you doing?
Exceedingly well. How are you?
Right. So David is running a bit late. He just messaged me. He should be here within 4 minutes. So apologies for that. If you have any questions for me, happy to answer. So we have registration open for next year. That is, we are open for year 10s and for year 12. So basically, all students who are now in year 9 or in year 11, they can join. So if you know anyone in year 9 or year 11, if you please ask them to join COMPOS. And it would be great if you remind your teachers of COMPOS and urge them to for the students to apply. So yeah, so we want a lot of. We are still doing year 11, but because we have so many year 12s, we won't be taking on more year 13s. Okay, so you guys will go to year 13, but we won't take new year 13s. Well, probably not. Depends on the numbers, of course. We're planning to have approximately 120 year 13s. Yeah, you don't need, if you've completed year 12, you don't need to reapply. So if you've done 75% and you're willing to go forward, then yes. Yeah, that's an important question. I think I need to mention that to everyone. But if you're not on the course for some reason, and but you've been following along, and if you've been attending webinars, we can admit you to year 13. Right. Year 13 will only be for a few months. So year 13s will finish in January. So this year, year 13s finished in May, and we think that's too late. So next year, year 13 will only run to January. So you'll have enough time to do your exams, in preparation, etc. No, Ben. So the next assignment, we have two more assignments to go, assignment 11 and assignment 12. Assignment 11 is going to be on, the maths is going to be on inequalities. And assignment 12, oh, I have it in front of me. Combinatorics. And for physics, it's simple harmonic motion, a big topic, and electrostatics and capacitors. It's two quite difficult topics, but also exciting because, well, simple harmonic motion is simply exciting. In year 13, you will have 6 assignments. Six for math, 6 for physics, and 6 for maths. In year 12, 12. David is here.
Hello. Hi, Vlad. Can you hear me? Hello? Can you hear me? Super. Brilliant. Let me just see if I've got the rights to share my screen.
Can anyone hear David?
We can hear.
I cannot hear.
Some people are saying yes, some people are saying no. Shall I leave and rejoin?
Oh, okay, I can hear you. Yes, I think everyone can hear you now.
Excellent.
Right. So just a second, did you hear me before? Oh yes, you did hear me before. That's very weird. Okay. Yeah, that's yes. Thank you. To you, David.
I'm the host. So I should be able to share. Oh, a minute. I just need to go and grab my stylus. Give me 1 second.
Well, we get a grade for COMPOS. Well, you don't get a grade for COMPOS, but you can get a letter of completion if you wish. You just ask me directly, and I will write you a letter.
Right. Are we ready to start? Or
Yes, I can't see you, David. Can anyone see David?
Oh, I had this problem yesterday that my camera wouldn't. Let me close Teams. Teams sometimes. Shall I start? I've just left Teams. I'm just going to leave and rejoin. Is that okay?
Yeah.
I'll make you.
Exam practice. Well, maybe. We're not 100% sure. So we have the paper, but the value of it is somewhat questionable. So we are not sure whether we want to add it to the syllabus or not. Still can't see you, but could you try sharing? Maybe. Okay, we can see your screen.
Okay. Okay.
But we can't see you, unfortunately. Well, I'll hand it over to you, David.
Okay, I'm sorry you can't see me, and then I'm just a sinister black presence. I'm going to go through questions from the analysis of function sheets, and I'm going to start with this, which I think is the I think this was my first involvement with COMPOS. I think this is the first. Am I one of the authors? Yeah, I think this was the first sheet I wrote. Must have been this time last year. And I'm going to start with problem number 2. This is a very, very nice question. So it says, sketch the following function. And it says, f of x is cosine of arc cosine of x. And the very naive thing to do is to just think, right, well, cosine and arc cos are function and inverse, so the function is going to be x. Now, on some level, so this is kind of what I've written here in green is naive. Okay, and so this is not what we want to write. Okay, and I'll look in more depth at why or sort of other circumstances where this is even more wrong. So we can't just say cosine and arc cosine x are function and inverse. What we really need to do is think about domain and range. So the first thing to notice is that arc cos as a function is only defined on the range -1, 1. And it maps onto angles that lie between 0 and pi. Okay, and it's just to focus our attention, it's worth mentioning, just sketching what arc cos looks like. So arc cosine of -1 is the angle whose cosine is -1, so that's pi. Arc cosine of 0 is pi over 2, and arc cos of 1 is 0. So arc cos is a decreasing function, and I've not drawn it particularly well, but it's a cos wave on its side. So it goes through the points 1, 0, 0 pi over 2, and -1 pi. Now, if we restrict to this domain, then we know that cosine and arc cos are function and inverse. So on this, it's worth noticing that this arc cos function here, which is the first function that we evaluate, is only defined on the range -1, 1. So if we were to use values of x outside of that range, the arc cos function would not be defined, but there's no such thing as arc cos of 2. Okay, as long as we restrict to that domain, arc cos spits out an angle between 0 and pi, and then the cosine function on the outside just maps that back to x. So what we end up with is that f of x is indeed x, but the domain is -1, 1. Okay, and that's now the correct. That restriction of the domain makes this correct. Just as a nice comparison, I'm just going to look at a question which is not on the sheet, but let's imagine that we had function k, which is arccos of cosine x. Now, what's the domain here? So the first thing to notice is that the first function, cosine x, is defined for all real values. So I've just got this cosine wave, which goes on forever. Okay, so this is 0, 1. This is 0. This is pi by 2, 0. This minimum is at pi -1. Then we've got 3 pi over 2, 0. Then we've got 2 pi, 1, and so forth. So the output of cosine x is the range. So the range of cosine x is y is all values within the interval -1, 1. So straight away, arccos is going to be defined within that interval. So arccos cos x makes sense. But notice that arccos always maps into the range of angles, which is 0 to pi. So let's look at what happens in the different sections of the graph. So in this section, which I've highlighted yellow, where the x values are between 0 and pi, the range of values of cos x range from a minimum of -1 to a maximum of 1. And arccos maps those angles into the range 0, pi. So on this highlighted yellow section of the graph, arccos of 1 is 0, arccos of 0 is pi by 2, arccos of -1 is pi. So we just get a straight line section, and this is y is equal to x. If we were to now look at the next section of the graph, which goes from x values between 0 and pi, the y values go between -1 and 1. Now, when we perform the function arccos has got no way of knowing, this function arccos has got no way of knowing that these values between -1 and 1 came from x values between pi and 2 pi. It just simply follows the rule of spitting out an angle between 0 and pi. So the output from arccos of, let's say, 1 at this maximum is not 2 pi, but is back to being 0. Arccos of the 0, which occurs when x is 3 pi over 2, doesn't give me 3 pi over 2, but gives me pi over 2. So what we get in the green section is a straight line, okay, and it'll be the straight line y equals 2 pi minus x. Now we're kind of done Okay, because each subsequent cosine wave is, cosine is a periodic function. So k is also going to be periodic. So what we're going to get is just this sort of tent function repeating. So we're then going to get similar straight line sections. So I just clicked away my axis away. So 0, 2 pi. This would be 3 pi. And this would be 4 pi, and so on. Okay, so we don't, in this instance, we don't get arc cos x is x, but we get a kind of sawtooth function. So k is the periodic function with period 2 pi, such that kx equals x when x is between 0 and pi, and kx is 2 pi minus x when x is between pi and 2 pi. Okay. I won't spoil the question on the sheet, which is gx being arc sine x, but the question on the sheet is similar to, that's going to be similar to arc cos x. And then the final example it asks us to consider is hx is arc sine cosine x. Okay. Let's have a look at how we would approach this. So first of all, I can sketch my cosine wave. So this is 0, 1. This is 2 pi negative 1. And then I think about what arc sine does. I'm just going to consider this first section of my cosine wave between, this is not 2 pi, this is pi. Okay, and then this is 2 pi 1. Okay, so I'm considering the first period of my cos wave. So this is y equals cos x. It would also be useful to consider what the graph of y equals arc sine x looks like. So arc sine is defined again on the interval -1, 1, and it returns the angle in the range minus pi over 2, pi over 2, whose sine is given to that, is equal to that value. So arc sine of 1 is pi over 2. Arc sine of 0 is 0. And arc sine of -1 is negative pi over 2. So we can consider tracing this graph here. So if I was to apply the arc sine to the different values of my cosine graph, when the output of cosine is 1, arc cos of 1 is 0. Arc sine of 1 is pi over 2. When cosine x is 0, arc sine of 0 is 0. When cosine outputs -1, arc sine of -1 is minus pi over 2. So the first observation is, as my cosine wave covers the values 1 to -1, my values of arcsine go from pi over 2 to negative pi over 2. So the orange part, sorry, the shaded yellow part of that wave where the x values are between 0 and pi starts off at pi by 2, then crosses 0, and then goes to negative pi by 2. Now, what I have sketched here looks like a straight line. And this is an important point to think about when you sort of submit work and when you write work, okay, is I've drawn this as a straight line, but at the moment I've done nothing to justify that it is indeed a straight line. Now it turns out that it is, okay, and it may well be that your intuition tells you that it is, but what we need is some justification that this section of the graph really is a straight line. So let's try and prove this. Okay, so let's first consider x in the region 0 pi over 2. Okay, so what I can do here is I can draw a right angle triangle with angle x, and this side length on the bottom, OA, is the adjacent side to this right angle triangle. So the length OA is cosine x. Now, arcsine of cosine x, and this is the sort of key to this question, is the angle whose sine is in the interval 0, well, is in the interval minus pi over 2, but cosine x here is going to be positive. So the sine is going to be in the interval 0 pi over 2, is the angle whose sine is the angle in the interval minus pi over 2, whose sine equals cos x. So we want an angle y in this sort of principal interval where sine y is equal to cosine x. And if we look at this diagram, we can convince ourselves that this side length cosine x, which is the adjacent of the angle x, is the opposite of this angle up here, which is pi over 2 minus x. So what this diagram shows, so the above diagram shows that arcsine cos x is equal to pi over 2 minus x, if x is in the interval 0 pi over 2. Okay. And so what that shows is that this section of the graph here is pi over 2 minus x. Now, again, in terms of your write-up, it should be noticed that this argument here is necessary to prove that it's a straight line, but this is only valid for x in the interval when x is in the interval 0 pi over 2. So what we really need to look at now is what happens when x is larger than pi over 2. And let's look now at x in the range oops. My screen is frozen. 1 second. My screen. Everything is frozen. I'm back. Okay, so now let x be in the range pi over 2 pi. So now x is this angle here, which is obtuse. If I consider y to be the supplementary angle, so pi subtract x, then this length, this horizontal length here numerically is equal to cosine y. And now arc sine of cosine y, by exactly the same argument, is going to be this angle up here, which is pi over 2 minus y. But now note that cosine y is the sort of numerical, is the absolute value of this length. What we really want is arc sine cosine x, and cosine x is going to be negative, and it's going to be the negative of cosine y. And because arc sine is an odd function, as we can see from the graph here. Okay, and in terms of your write-up, it's really important that you're including all these justifications. So this is because arc sine is an odd function. So arc sine of minus cosine y is the negative of arc sine cosine y, which we just decided was pi over 2 minus y. So that's y minus pi over 2. But y is pi minus x. So this is pi minus x minus pi over 2, which is equal to pi over 2 minus x. Okay, so what we have here is, this is the argument for x being an obtuse angle. So this is in the range pi over 2 pi. And we've got that arc sine cos x is still pi over 2 subtract x. So this section here is enough to convince me that this yellow part of the cosine wave maps to a straight line. Okay, but the justification of the two bits of the straight line needs a slightly different geometric argument. Okay, so where I'm up to here is I know that the yellow part of the curve goes to a straight line. I've now got symmetry. So cosine x has a symmetry in the line x equals pi. That means that the output is going to have the same symmetry. So the graph on the green, for the green section of the shaded green section of the curve, is going to also be a straight line, and it's going to be symmetric in the line 0 pi. So 2 pi goes back to pi over 2. And this is by symmetry in the line x equals pi. Okay, and now we're done, because now we can use periodicity. Okay, so the cosine wave is periodic. So cos is periodic. With period 2 pi. Arc sine cosine x is the periodic function with period 2 pi, such that y is equal to pi over 2 minus x on for x between 0 and pi. And then it's y is equal to minus 3 pi over 2 plus x on x between pi and 2 pi. So what we get here is a sawtooth function. And so the first sawtooth is this down and up. And then it repeats. Okay. So for a complete answer, the first part is to get the sort of general shape that arc sine just goes down. Then there's a bit of geometry to guarantee that it's a straight line. We need to work a little bit differently we need a geometric argument to make sure that we cover acute and obtuse angles. And then we need symmetry to back up our intuition that it's just going to sort of come back up in the same way. Okay, so that is a thorough presentation of problem number 2. Does anyone have any questions about problem 2, or are people happy for me to continue? If people are happy for me to continue, just put a thumbs up into the chat. Good, good. Okay, I'm going to look now at problem number 6. Which I seem to remember was a very similar version of it, was on a math paper, recently. So it says, using the definition of the derivative as the limit f dash x equals the limit as h goes to 0 of f of x plus h minus f of x over h, show that if f of x is a differentiable even function, then f dash x is an odd function. So the trick here is just to write a nice sort of compelling proof. And a good way to start is to draw a picture. So let's draw an even function. Okay, so here's my even function. And let's consider the derivative. Now, the hint here is that the derivative at a point x is the limit of the gradient of the chord. So I've just drawn a chord here where the x coordinates of the 2 points are x and x plus h. And then I've drawn a straight line through the two. And I've calculated the gradient as the rise, which is f of x plus h minus f of x, over the run, which is h. So the gradient of the chord AB is f of x plus h minus f of x over h. So that's the gradient of the chord AB. Now, I want to show that my derivative function of my even function is odd. Now, to show it's odd, I want to be able to consider what the derivative is going to be at the value negative x. So what I'm going to use is I'm going to use my symmetry property to just know that I've got an axis of symmetry in the y-axis. So I can reflect my points A and B across the y-axis back to A dash and B dash. Okay, and now I can draw a very similar picture. So I can draw this triangle A dash B dash. Now the two triangles are congruent because I've just reflected in the y-axis. But what's happened to the gradient? Well, the gradient of chord A dash B dash is, well, the run from negative x plus h to negative x is still h. But the rise is now the opposite sign. Because the heights are the same. Okay, but they're in the opposite sense. So the graph has come down. Okay. What we want to do now is we want to look at the derivative of the function at negative x. So f dash negative x. Well, that's the limit as h goes to 0 of the gradient of a dash b dash, but that is f of x minus f of x plus h over h. But that is just the negative of the limit of the negative value. So just flipping the sign and taking the minus sign out. But this limit is exactly the limit of the gradient of the chord AB, which we know is f dash x. Okay, so f dash, the value of the derivative at negative x, is the gradient of the chord a dash b dash as a dash and b dash approach one another. But the gradient of a dash b dash is just the negative of the gradient of AB. And then in the limit, the gradient AB goes to f dash x. Okay, so therefore, f dash negative x is equal to the negative of f dash x. And I think this picture is very compelling because whatever tangent I would draw over here at x, when I reflect, I just get a tangent which has got the opposite gradient. Okay, so the derivative function has got this relationship, and this is precisely the relationship that f dash is an odd function. Okay. If you never drew a picture, okay, and you wanted to just do this completely algebraically, we could say that f dash negative x is the limit as h goes to 0 of f of negative x plus h, subtract f of negative x over h. Then I could use my oddness criterion to flip the sign of the argument of the function on the inside and put a minus sign outside. So this becomes negative f of x minus h plus f of x over h, which I could write as the limit as h goes to 0 of f of x minus f of x minus h over minus h with a minus. And then this fraction here is just the fraction that you get when you do differentiation by first principles to get f dash x, but instead of using positive h, using negative h. Sorry, and I've got my signs a little bit wrong. The fraction would be f of x subtract h minus f of x. Yeah, because then I've got that gives me the right. That gives me the right signs. And so that is minus f dash x. Super. Okay, and then the questions say show similarly that the derivative of an odd function is even. Okay, I'll leave that as an exercise. It's a very, very similar it's a very, very similar calculation. Okay, any questions about that question? Or if people are happy to continue, put a thumbs up in the chat. If people have got a particular request for any of the questions on the sheet to go through, also put that into the chat as well. Otherwise, I'll just pick questions which I remember being interesting. Cool, we're getting some thumbs up. Ooh, I really like the look of problem 8. I like this thing of symmetry, and I've got a feeling that question 8 is similar to an old step problem. So let's have a look at problem 8 together. Okay, so let's have a look at what it asks me to do. So the first thing it does is it gives me a polynomial. It says the polynomial f maps R to R is defined as f of x is x to the power 4 minus 12x cubed plus 48x squared, take away 72x plus 22. And it says, show that the derivative of f at 3 is equal to 0. Okay, so for part A, the natural thing to do is to find f dash x, which is 4x cubed minus 36x squared plus 96x take away 72. And I can take out a factor of 4, that's x cubed minus 9x squared plus 24x minus 18. Right. What is f dash 3? Well, it's 4. 3 cubed is 27. 9 times 3 squared is 27. This is not coming out to 0. Four x cubed, 36x squared, 96x minus 72. Oh, no, wait a minute. 9 times 3 squared is minus 81. Plus 72. Take away 18. Yes, and that is 0. Okay, as desired. Okay, so f dash of 3 is equal to 0. So that's the first bit. Now, how are we going to find the x coordinates of the other turning points? So far is we know that 3 is a root of the polynomial x cubed minus 9x squared plus 24x minus 18. And hopefully, if I asked you to put into the chat what to do next, the little alarm bell would ring in your head that if you know a root, we can also find a factor. So we know that x need a negative 9x squared, so I need a negative 6x. That would give me an 18x. I need a 24x, so I need another 6. Okay, so my quadratic factor is x squared minus 6x plus 6. So I've got f dash x is 4, and then I've got a factor of x minus 3, x squared subtract 6x plus 6. So the turning points occur when x equals 3, or when x squared minus 6x plus 6 is equal to 0. This quadratic doesn't factorize nicely, but if I add 3 to both sides, I can complete the square. So I've got x minus 3 squared is equal to 3, which gives x minus 3 equals plus or minus root 3. So I've got turning points at x equals 3 minus root 3, x equals 3, and x equals 3 plus root 3. And then it says, hence find the exact coordinates of all the turning points and determine their nature. Now, I hope you forgive me. After a long day at work, I'm not going to substitute these values back into this quartic, but to get the y values, I would need to substitute back in. To determine the nature, however, I will do that. So my f dash x is a cubic, and I'll call the roots, I'll call this small root alpha, this big root beta, and the roots are at alpha, 3, and beta. And to get the nature of the turning points, I'm just going to consider the sign of the derivative in each of the regions. So if x is less than alpha, all 3 of these brackets, x minus 3, x minus alpha, x minus beta, are negative. So I've got 3 negative brackets, which give me an overall negative, which means the curve is going down. When x is larger than alpha, but smaller than 3, the first bracket becomes positive. The other 2 brackets remain negative, so I get an overall positive gradient. So my curve is coming up. If x is bigger than 3, but smaller than beta, the first 2 brackets are positive, but the last bracket is negative. So I get an overall negative gradient, and then eventually all 3 brackets are positive. So I end up with a overall positive gradient. Oh, my computer's frozen again a little bit. Notice that as across each of the critical points, oops, where's my, sorry, my computer's playing up a little bit. Across each of the critical points, exactly one of the brackets changes sign. So we just get alternating signs for the gradient. So we get a minimum then a maximum, then a minimum. And notice that the quartic is going to be sort of bowl shaped, so that makes perfect sense. And here we can substitute in to get the y values. Now, part B, I think, is a very good illustration of the difference in challenge between what you get at A level and what you get in a MAT, PAT, STEP paper. Because part A, albeit that the numbers are a little bit horrible, and even I've sort of said I don't really fancy doing the just algebraic chore of plugging these surds back in. I probably could. But this part A is just a, albeit on the sort of involved end, this is just A level. But part B requires an idea, okay? Because it's not really particularly familiar how to show that there is a vertical axis of symmetry. So let me draw my graph. And I'm not claiming this is the graph of f of x. I've just drawn some graph. And this is the line x equals 3. What we need to do before we can make any progress on B whatsoever is try and figure out what having a vertical axis of symmetry would actually mean algebraically. So what algebraic condition do I need to show? So having drawn the graph, I think things become a little bit clearer. That what I need to do is show that if I was to start at an x value of 3 and let's go forwards y, so I consider the point 3 plus y, then the y value, maybe y is a bad choice of letter. Let's call it 3 plus u. Then this y value up here, if there's an axis of symmetry at x equals 3, I get the same value of y if I go backwards u. Okay, so for part B, we need to show that f of 3 plus u is equal to f of 3 minus u. Okay, if this is exactly the condition to show an axis of symmetry. Okay, so all I want to do now is I want to get an algebraic expression for f of 3 plus u. Now, just before I do that, it's worth putting this into some context of what this is doing geometrically. F of 3 plus u, and I think my camera is off, so I was doing some actions to illustrate my point. F of 3 plus u, you'll recognize from GCSE, is a linear transformation of this graph. If I was to plot the graph y equals f of 3 plus x, it would be a shift of this graph 3 units to the left. So what this condition is saying, that if I was to shift the graph 3 units to the left, that moves my axis of symmetry to the y-axis. But if I've got an axis of symmetry in the y-axis, that's just our old-fashioned condition of being an even function. Okay, so when I find f of 3 plus u, if I end up with an even function, I should be happy. Okay, so here I've got my expression for f of x. So f of 3 plus u is, oh, my computer's frozen again. So f of 3 plus u is, oh, my computer is frozen again. Let's wait for it to unfreeze. Right, is 3 plus u to the 4 minus 12 3 plus u cubed plus 48 3 plus u squared minus 72 3 plus u plus 22. Okay, so notice that there's no sort of particularly elegant way of doing this. We just need to expand each of these brackets. And again, that's something in STEP, MAT, PAT, we just have to get a sort of proficiency for. So let's open this using the binomial expansion. So we end up with the first one, we've got 3 to the power 4 plus 4 times 3 cubed u plus 6 times my computer. Plus 6 times 3 squared u squared plus 4 times 3u cubed plus u to the 4. Then we want to subtract 12 times 3 squared. And I'll just put that under the units. Then I want to subtract 12 times 3 times 3 squared u. Then I want to subtract 12 times 3 times 3u squared. Then I want to subtract 12u cubed. Then I want to add 48 times 3 plus 2 times 3 times u. Sorry, times 48. Times 2 times 3 times u. Then plus 48 u squared. Then I want to subtract 72 times 3 and 72 times u. And then I want to add 22. Okay, so that is, if I just now evaluate these sums, we've got 81 plus 4 27s, that's 108 u, plus 6 times 9, that's 54 u squared, plus 4 times 3, that's 12 u cubed, plus u4. Then I'm subtracting 12 times 3 squared, so that's 12 times 9, so I'm subtracting 108. Then 12 times 3, that's 36. myself. So now minus 216 minus 72u plus 22. Can you still see my screen?
No, we can't.
Let me just share my screen again. The host has disabled my screen sharing. I'll just send a message to Vlad. Yeah, I wasn't enjoying that part of the conversation. That part of the calculation was just a little bit of a chore, but sometimes you need to do that. The key part to that question was that first bit of recognizing what calculation we'd need to do to establish symmetry. I don't think you can see my screen yet, but you know, I was simplifying that polynomial. What do you think will happen? What should happen if I've got the calculation right? So in a moment, I'm just going to sort of like, you know, simplify all of the terms. What am I looking out for in order to convince me that I really have got the right polynomial in the end? I'm just going to try and find Vlad's. Excellent. It should just have even powers. So those odd powers, the u and the u cubed, should go away. Notice as well that when I just get the even powers, it should be easier for me to calculate the y value when I put in the 3 plus root 3 and the 3 minus root 3, because the y value at 3 plus root 3 will just be the y value when u is root 3. But I won't get any nasty surds because I'm just going to have even powers. Let me just try and find Vlad's number. Does anyone have any requests for which question to do after this one? Oh, where's Vlad's number?
It's not really a question, but could you sort of give a bit of insight how they arrive at like the hint from question 10?
A hint from question 10. Yes, I think I can. So I think the first thing to say is that notice that the sort of a cubic function, forget sort of forget the sort of translations in the y sort of direction up and down. If you think of its derivative is going to be a quadratic function. So every cubic is the integral of a quadratic. But if you think of every single quadratic, you can complete the square and you can get this symmetry. So every single quadratic, is just a sort of, is just a parabola with a vertex of symmetry. Now, if you integrate that quadratic, imagine starting at that vertex, or alternatively, just shift the curve so that vertex is at the origin, say. You've got a symmetry. So on one side of the vertex, you've got a positive gradient. So when you integrate it, you've gone up. On the other side of the vertex, you've got a positive. When you integrate it, you're going to get negative values because it's going to go up, but it's going to be going up by the same amount on the left as the right. So what you've got is an odd function. So what that then shows is that the amount that you've gone up from that vertex when you integrate is the same as the amount that you've gone down when you go in the other direction. Now, that odd symmetry is exactly a rotational symmetry by 180 degrees. So if you sort of start your cubic off at the vertex of your quadratic, so you move the vertex of the quadratic to have x coordinate 0, and then you move your cubic up and down to be at 0, you're just going to get an odd function which has got a rotational symmetry. So what the intuition in question 10 is that if you do the right kind of translation of a cubic, you will end up with an odd function with 180 degrees symmetry. Does that make any sense? I'm just waiting. I've sent a message to Vlad. Any other questions while we're waiting for me to get back onto the Zoom?
For the question you just did, I was wondering if you were to show that the derivative could be translated by -3 to get an odd function, wouldn't that then show that it's an even function when it's translated by -3, therefore also arrive at the same conclusion, just with less complicated subbing in?
Yes, that's a very good idea. Yeah, what you'd want to do there though is you would need to do the integration, but then if you've written your sort of derivative as a sort of power